Hello everyone, welcome back to my YouTube channel. Today I am going to show you how you can do a thermal simulation of two battery cells, or you can say conjugate heat transfer simulation. Suppose we have two battery cells, lithium-ion battery, and they are being cooled down by a fluid which is passing across these two battery cells. This fluid can be air or can be a dielectric fluid. Maybe we will consider air in this case. For this simulation, we can take advantage of symmetry analysis, and we will be simulating only one of the half, which I can show you over here. Let's go to the meshing, but before that, we can do meshing in two different ways. We can create a conformal mesh or we can create a non-conformal mesh. Today, I will show you how you can use a conformal mesh. Conformal mesh is a little bit beneficial, as in that case you don't need to bother about the contact. If you use non-conformal mesh, then you have to take care of the contacts between battery cell and the fluid. For creating conformal mesh, you have to create a shear topology. For that, go into workbench, and here is an option for the shear. Press this shear and it will show you the surface that would be used as a shear topology, and click enter. Let me show you. If you hide this fluid, and you can see this purple sign which is indicating the shear surface between these two. Same you can see on the fluid side. Let's check over there, and you can see surface is being sheared between these two bodies. And other thing, by right clicking you can deactivate some of the part or some of the geometry, and they won't be transferred to the meshing. So let's go to the meshing now. Here is our geometry in Ansys meshing. First, let's assign some name so that we can take the benefit of name selection in meshing. So this one would be our inlet, and so I will be giving name mesh flow inlet. This one is our outlet. I'm using shortcut for the name selection. You can do by right clicking, and here is the name selection, or you can press N, as you can see over here. I use this shortcut normally, and that is our outlet. Let me hide these two, and I want to give all these wall a name so that I can use these bodies for creating inflation layers. Let me call it inflation layers. And another thing, let me show all bodies. This one, this one, this one, and this one, all these are symmetry. Now first let's generate the default mesh, then we can play around with the settings so that we can have a better mesh. And let's generate mesh. Here is our mesh, and that looks pretty good. I would like to have little finer mesh on the fluid side, and then we will create inflation layer on that side. For that, let's go into the meshing, and I would say insert sizing. I will use this fluid, and the element size in the maximum size is 2.4 millimeter. So here I will use 0.5, and let's see what we get. Still it is not good enough, and I want to use one more setting over here. Capture proximity, I would say yes, and in proximity I want to have at least 5 cell. Proximity would be this one from here to here. Whenever you have a narrow surface, that would be used as a proximity. And let's see what we get after that. Yes, exactly. That's the problem with the shear topology. Here you can see over here on this side the element size is much bigger. So here the element size is same because we are using shear topology or the conformal mesh. And here you can see the size is decreasing rapidly, because on the fluid side I want to have much finer mesh as compared to the solid, but in conformal mesh you have to have the same element size on both sides. Either I have to go with the non-conformal mesh, or I have to use the same sizes on this side. And for that, I have to reduce the element size on this solid body. As I said, I would be going with the conformal mesh. Let's reduce its size. And here element size, maximum size 0.5. Let's keep it 2, and this one is element size is 0.5. And hopefully we will get much finer mesh on the solid side, and then we can apply inflation layers. But the problem, I think, is pretty much clear with the conformal mesh, so that's why you don't go with the conformal mesh or the shear topology when you have complex geometry, or where you want to have the different mesh sizes on two sides of the solid. Little better, still not satisfied. I think we can work that, or we can make it a little smaller. I think this one should work, and then we will add inflation layers. If you have computational power and enough resources, so you can go finer mesh, but otherwise you have to decide by yourself, does it make sense for you or not really. And let's see how many elements we have. So these are already over 2 million. I don't like this much finer mesh, but let's see, I think I can work with that. Let's add layers. I think when you will add inflation layers, you won't get hexa mesh. Let's check. I think it will convert into polyhedral mesh. Name selection, and we have name selection of inflation. There seems a problem. Okay, some names are extra, which is from previous simulation. I'm deleting those names. Okay, this body is over here, and here I want to have inflation layer. So now let's generate, and I want to have 4 inflation layer on both sides. And I think now it will convert into tetrahedral mesh. Okay, that's how my mesh looks like. It is pretty fine. So I would try to make it little coarser. After refinement, that's how our mesh look like at the interface and the battery cell. For solid body, this mesh is quite fine. You can use coarser mesh, but for the timing, I am going with that, because with the conformal mesh, I cannot make it coarser. So I think that's okay. I have resources, so I can use this mesh. But let me show you something. If I hide this body, for example, I'm hiding this body, and here that's how my mesh look like at the interface. But here you can see I got the conformal mesh. In connection, you can see this green tick, because we have shear topologies. The contact have been handled automatically. We don't need to do anything. Now we can move to Fluent. Here is one really important thing. In name selection, in inflation and symmetry, one thing you can see in inflation and symmetry, we have this surface and this surface. It is present in both name selection. So if you will move like that in Fluent, you will get error. You have to make sure that the same surface you don't use in two different name selection. So you are using over here, what you can do, you can say this inflation. Here you can say do not transfer to solution. Send to solver, and you can say no. Now we can close this one. Otherwise you would get error. Okay, we got our geometry in here, and he has placed these two in the wrong type. So you can see fluid, and it is saying cell is a fluid. So we can change its type to solid. Similarly, and we can say this one is also a solid. Now we can set our condition. Energy equation is on, so we will be doing thermal simulations. Energy equation should be on. The flow would be, I would be using a liquid. In liquid we will get a laminar flow. and here I have already, no, sorry, not here. And then you would go to material. The cooling fluid I have already defined with these properties. Then I have defined two cells, and in cell I have defined two material with the cyclic orthotropic properties. Density of the cell lithium-ion battery, so density is approximately in this range, specific heat in this range, and then thermal conductivity. It is cyclic orthotropic. In cyclic orthotropic, you have different thermal conductivity in axial, radial, and tangential direction. Let's go in here. Here, this z-axis, this one shows our axial direction. In axial direction, we have 25. In tangential direction, also 25, and in radial direction, 2. What is tangential direction? Let's see. So here is our battery cell. Axial direction would be from along the axis from top to bottom or bottom to top. Radial direction from center towards outside. And in tangential direction is the in term of coil, because you know that lithium ion battery have the jelly roll in the form of coil, and thermal conductivity is defined in these three directions. So in tangential for the lithium ion battery is different, and that is also the same as in the axial directions. And one more thing, here you have to define your axis for each cell. Let me display those cells. The both cell, they have different what it's called, they have their own coordinate system, because we are defining cyclic orthotropic property. For cyclic orthotropic thermal conductivity, you have to define coordinate for each battery cell separately. If you use the same origin for the both of these battery cells, your property will be incorrect, or you will get incorrect result. So that's why when you go over here in the cell, not cell 1, let's go to cell 2. In cell 2, if you go to orthotropic property, x is origin, x is at 0, y is at 0.022 meter, and z is also at 0. These coordinate I had calculated in space claim, and z is equal to 1. This represent the axis of this battery cell. Similarly, if you check other one is at the origin, and for that's why I have 0 0 0. Imagine if you have 10 or 20 battery cell, it will take a lot of time to define these battery cells or these materials. For that, you can take the help of text user interface. For that, I have a separate video series where I have shown you how you can use text user interface to define material in such cases. Anyway, we have defined over here. Let's assign materials. Cooling fluid is over here. Now let's go to this one. It should be cell 1. For thermal simulation, you have to define heat source. So either you can take the help of this battery model, where you can define electric current or electric potential. If you don't want to use electric current or electric potential, you can calculate joule heating outside this simulation by using with the help of I square R. Yeah, I understand the R is normally not constant for the entire range of SOC, but for the sake of simulation, we can approximate, because from 20 to 80% SOC R approximately remains constant. So you can use for heat generation I square R. But if you want to use a thermal dependent property, so there you need to have some profile, or you have to use some UDF. But for the timing, we are saying, okay, we have constant heat generation. As I said, either you can use this battery model to use electric potential equation. If you don't want to use, you can calculate heat generation outside this simulation, and you can use heat source as an input. To define heat source as an input, you would go to your material. So you go to material solid, this cell, and here first check the material name. This one is the cell. So it is cell 1, And then for heat source, you activate source term. When you activate this source term, you will see this one will be activated. Go in here, and here now you have energy sources. So for the timing, you can see there are 0 sources. Go to edit, and here you can define how many sources you want to have. We want to have one heat source. When you will say one heat source, you will see one. If you will say two, there will be a two. Three, so you can see three. So we want to have one heat source. Then you will go to drop down. Here you have different option. Either you can use constant, expression, or input parameter. For expression and for using heat source as a profile, I have a separate video, you can check that, but today I will be using the constant heat source. Here is the constant, and then you can define heat source in watt per meter cube. Here you have to be careful. When you use I square R, you get heat generation in watt, but here you need to define in watt per meter cube. You will calculate heat generation in watt, and you will divide it by its volume. Then you will get watt per meter cube. So I am just putting one number, 100,000. Normally in watt per meter cube, it is in this range for 1 or 2 watt. So we have this heat source. You will say OK, and one of the heat source has been defined, and apply, close. Same you would do with the second one. Here cell 2 is fine. Source term, in source term, edit. I want to have one source. You will go in here and you would say I want to use constant. And here again 1, 2, 3, 4, 5. 100,000 watt per meter cube. OK, apply and close. And other thing, I normally set my units. For temperature, I mostly use Celsius, so I would be setting it is already in Celsius, and I would be using mass flow rate, mass flow in gram per second. Yes, that's fine. We have defined material, we have assigned this material to cell zone, we have defined heat source. Now we will go to boundary condition. In boundary condition, we have so mass flow inlet, he has considered it as a wall, so we can change its type and we can say it is mass flow inlet, and that is our inlet. In inlet you can set mass flow rate, it is in gram per second, 2 gram per second. Then we have to define the temperature. The fluid will be entering at 25 degrees Celsius. Apply. Here is our outlet, that's fine, because and at the outlet 0 Pascal, and that's perfectly fine. In internal you don't need to do anything, and you see there is no interface. There shouldn't be any interface as we are using the shear topology. Close this one. There are some name expression, okay, that I had used for some other simulation. You don't need to bother about that one. Then report definition, you can define a few things. Let's define some temperature that we want to follow. Volume average, we want to see how the temperature of the cells change. So I would say cell 1 temperature, and yes, volume average, I want to follow the temperature, total temperature of the cell 1. Okay, and similarly I would copy. For report definition, you can check my other video for detail, so I'm not going into the detail over here. I will provide the link in the description. We have defined two reports to follow the temperature. Not like that, I want to have it cell 2 temperature. We can follow this report definition in a report plot. So we will create a new one, and we can say cells temperature and cell 1 and cell 2. You will see what this will do if you don't know about this one already. Here I have defined the report for cell 1 temperature, cell 2 temperature, and outlet temperature. Now everything is set, and we can run simulation by right clicking, run calculation, initialize, and calculate. You can initialize separately from here, or you can by doing that initialize and calculate. And before that I have defined 3 report, and I am checking what is happening in these 3 reports. We will see what will happen. Right click and initialize and to this one. That's pretty good. Now here you can see I have defined these 3 reports, and I said I want to plot the temperature of these 3, and you can see during simulation I can plot these 3 temperature, and I can check how these are changing. For detail of report definition, you can check my video. I will provide the link in the description. Let it run. It will take some time. It is over here. Okay. And meanwhile, I have changed few things, and we can talk about something else meanwhile. At the end of the simulation, we want to check if our simulation is running correctly or the results are feasible. Here I have done something. This one is the volume of the cell. This one is the heat generation, and this one is the in watt per meter cube. I had changed the heat generation, and instead of 100,000 I have applied this one, which is corresponding to 4 watt. And as well as the mass flow rate, what I have given, that I have also changed. That is, I have given 1 gram per second, and this one is the joule per kg per Kelvin. This one is the heat capacity of the fluid. Here I am calculating expected delta T at the outlet, or the delta T between inlet and outlet. We know the mass flow rate, we know the Cp. At the steady state condition, this 4 watt should be transferred to here. So that I am using this one. Q is equal to M into Cp into delta T. You can use this formula to calculate the your outlet temperature. If it matches with this delta T, it means your simulation is running correctly. It means we are expecting a delta T of 2.66. And if I go back at the inlet, I had given 25, and it is somewhere 27 point little lower than 8, so it is in the range of 2.7 or 8, and so we can check after this simulation would be finished. It is going well, 2.44. It will be finished soon. Let's just wait a little bit. Our simulation has finished, so we can check our outlet temperature. For that, we can go into the bottom at report and surface integral, and we would say mass weighted average temperature at the outlet, and we can say compute. At the outlet temperature is 27.8, and let's check our inlet temperature. Our inlet temperature is 25, so there is a difference of 2.82, and what we were expecting 2.66. Difference is quite small. It means our simulation is quite good. There is a difference of 0.15. Yeah, that's perfectly fine. So you would get this much difference because of numerical calculation. You can reduce this difference by changing some setting. One of the setting, maybe I am using simplex, so with a couple you get more better solution, but I did not use because it is little bit slower. But in my opinion, 0.15 is not that bad. Anyway, we can check our results. We can go to graphic and we can see, we can check our temperature. There is no difference between static and total temperature in here. I just used to check, or I always check total temperature. We can select all of these bodies, and that's how temperature distribution look like. Here a few things. Here is our inlet, which is entering at 25, and here you can see outlet, which is at little bit higher temperature, that is 27.8. And these are the average temperature of our battery cell that you can also see from here, 34 and 37. Yeah, that's good. And one more thing that you can check over here, the temperature of the first battery cell is lower than the second cell. Yeah, that's good because this one is closer to the inlet and it is meeting a fluid with lower temperature. When fluid reach over here, the temperature of the fluid increases little bit. So that's why the temperature of second cell is expected to be higher than the first cell. That's how you can check and your temperature distribution, and you can see how this temperature is changing. Heat transfer coefficient is it good or bad, that you can check, or there is one thing I think that you can do. There is one thing: wall heat transfer coefficient, wall flux, wall stress, total surface heat flux, and surface heat transfer coefficient. This one is that you need to select, I think, these two walls. Oh, yes, this one is displaying the heat transfer coefficient of this surface. That's the heat transfer coefficient on this surface, 289 approximately. All of these, and okay, you don't need to check all these, only 1, 2, 3, 4. So here is the heat transfer coefficient on the surface, and the meshing was not good enough. That might change little bit, but you can play around with that one. And anything else? Yes, one more thing. Let's check the temperature only of the fluid. We want to check the temperature of only fluid, that is component 2, wall, mass flow inlet, and this one, and these are. That's the temperature of our fluid. So you can see there is a heat transfer from solid to fluid. And here we did not define any interface because we were using shared topology. Ansys-Fluent took care of this interface by itself. You can improve this heat transfer coefficient by increasing your flow rate and with playing around with different parameters. Anyway, that was the introduction of the heat transfer simulation, or the conjugate heat transfer simulation that you can do in Fluent. I hope you found this tutorial helpful. If you have any question, leave them in the comment below. I will try my best to reply. Thank you for watching, and see you in the next video.